number 14, we have a whole network of capacitors, and we're told the battery has a potential difference of 10 volts, and the 5 capacitors are each 10 microfarads. Two questions. What's the charge on capacitor 1, C1, and the charge on capacitor 2? Well, part A is actually pretty straightforward. Why? C1 is connected directly across the battery, which means it's eventually going to charge up to 10 volts, the same potential that's on the battery. We can use Q equals CV, just rearranging the capacitance equation, which is charge over voltage, and simply plug in the values. 10 microfarads, 10 to the minus sixth, times the voltage, 10 volts, gives us 1 times 10 to the minus fourth coulombs. And that's the answer to part A. Part B is a little bit more exciting. Why? Because C2, we don't know the voltage on it. It's part of a larger series. It's not charged to 10 volts. That 10 volts is distributed across this network. So before we can do anything else, we've got to figure out the capacitance of this whole side of this sort of network of things. To do that, we have to start from the inside out. These two capacitors are in series, one after another. And if you use the series capacitance equation, 1 over 10 plus 1 over 10 equals 1 over the capacitance, you'll discover that these two together are 5 microfarads. Those, in turn, are in parallel with this 10 microfarad. For capacitors in parallel, you can just add them up. In this case, that's just 15 microfarads. But then that is now in series with this bottom 10 microfarad capacitor. For that, 1 over 15 plus 1 over 10 equals 1 over the total capacitance. And if you do the math, you'll end up with 6 microfarads. So now we know this whole series of capacitors over here is equivalent to 6 microfarads. And so now we can actually figure out how much charge is going to flow out of the battery and over this side network. We already know that 1 times 10 to the minus fourth coulombs are going to flow over this way to charge that. But now we can actually figure out the charge that's going to flow over this way. How do we do that? Very similar way. To find Q, just C times V. In this case, the total capacitance of that entire size of the network is 6 microfarads. The voltage it's eventually going to charge to, the whole system, is 10 volts. And so that gives us 6 times 10 to the minus fifth coulombs. Now I'm going to write that a little bit strangely. Just trust me on this for a moment. I'm going to write it as 60 microcoulombs. I know it's not proper scientific notation, but trust me, because our capacitance is in microfarads, this charge in microcoulombs will make our life a little bit easier. Now, what do we know about this charge now? Well, we know that 60 microcoulombs are going to flow over that way. Now, when it comes to this junction, part of it's going to flow this way, and part of it's going to flow down this way. It's probably not going to split up equally because the capacitances are not the same. We've got 5 over here, we've got 10 here. But we do know is the charge is going to recombine, whatever charge flows in here, recombine and all flow down onto this capacitor. So we immediately know how much charge is going to be on this bottom 10 microfarad capacitor. It's got to be 60 microfarads. All the charge that flowed through the top two have to flow into that one. Once we know that, we can actually figure out the voltage on that bottom capacitor. Just rearranging the capacitance equation, charge over capacitance, gives us 6 volts. We know there's 6 volts across that capacitor, and so therefore, we actually can do a little bit of work up here. We know, therefore, that this has 4 volts across it. And you might say, whoa, wait a second, what's going on? Well, this point in the circuits is at 10 volts. This point in the circuit's at 0 volts. We usually make this point of the battery 0 volts, the negative terminal. And if there is a voltage difference of 6 volts across the battery, and it's 0 volts here, that means this point in the circuit right here has to be at 6, it has to be at 6 volts. Sorry, I almost paused here for a second. And that means the difference between here, 10 volts and 6 volts, has to be 4 volts left on this capacitor. this capacitor must be charged to electric potential of 4 volts. If we know that, we can now use the same equation, Q equals C times V, to figure out the charge on this capacitor. It's 40. The moment we know that 40 microcoulombs must have flowed over to charge up this one. And by deduction, you can figure out what remains must have flowed down this part of the circuit onto this capacitor. And believe it or not, we can immediately then claim there must be 20 microfarads on this capacitor. That is the final answer, but I want to take it one step further. That is the answer to B. If 20 microfarads flowed onto this one, that means 20 microfarads have to flow down through this one. As much charge enters one plate has to leave the other plate of a capacitor, which means this bottom capacitor is also at 20 microcoulombs, or has that much charge. And then if you work out the voltage on each one of these, they're both at 2 volts. Notice again, 10 volts, it would be 8 volts down to 6 volts, 6-volt difference down to 0 volts. No matter which path you take around this thing, you'll end up with a voltage drop of 10 volts equal to the voltage of the battery. I hope this helped. This one really was math Sudoku. Good luck. Talk to you soon.